Hi, everybody. I'm James Taylor. I think we're setting a record for the most speakers in a single speaking slot, so that's kind of exciting. So we're going to talk about, first we're going to start with 3 use cases, and we're going to go through those. Tom Verleen is going to talk about Argus, which is a time series metric alerting and monitoring platform that Salesforce uses. He's going to talk about how they leverage Phoenix within that. And then after that, Mas Suzuki is going to talk about how Sony is using Phoenix in their News Suite application. And following that, Vijay Vangapandu is going to talk about how eHarmony is using Phoenix in one of their most visited pages to reduce query latency pretty dramatically. And then we're going to switch gears and we're going to talk about a couple new features in Phoenix. One is Purna Chandra is going to talk about transactions in Phoenix through Apache Tephra. So that's kind of exciting. That's been released in 4.7. And then after that, Maryann Zhu is going to talk about cost-based query optimization in Phoenix using Calcite. So that's some new kind of ongoing work that's taking place. So tomorrow morning from 9 to 1, there's my pitch for PhoenixCon is happening at Salesforce. So that's at One Market. So you're all invited. It's free, RSVP. And I'm going to turn it over to Tom now. Thanks.
All right. Thank you, James. All right. So my name's Tom Verleen. I work with James at Salesforce. So I'm going to talk a little bit about Argus and what we're using Phoenix for with Argus. Argus is a time series alerting and monitoring system that we use for operational data at Salesforce. And originally, it ships out of the box by default with OpenTSDB. And OpenTSDB has performed pretty well for us in the past, but there are some limitations that we had to explicitly work around in the code that we wrote. So for those of you who've used time series and have specifically used OpenTSDB, one of the big factors is tag cardinality. So if you have time series data that has a high amount of dimensionality to it, OpenTSDB currently limits the number of dimensions that you can add through tags to a hard limit of 8. And furthermore, when you have tag data for your time series that has a large number of unique values, so say you have a tag that represents the number of hosts in a data center and it has values of 10,000 or more, we experience a pretty dramatic performance cliff when that number gets relatively high. Another limitation that we have is OpenTSDB uses a UID table to identify metrics and map metric names to unique identifiers. That has a hard limit of 16 million UIDs, which sounds like a lot, but when you're monitoring an enterprise like Salesforce that has multiple metrics coming from literally thousands of hosts and multiple data centers, you can exhaust this fairly quickly. Another limitation is that OpenTSDB does time series very, very well, but it's hard to join to other data sources. So one of the primary use cases is if you're monitoring performance and you want to correlate an anomaly that you see on your time series with log data or other performance metrics or other operational data that you collect. It's very difficult to do that out of the box with OpenTSDB. And it's really difficult to write a good transform grammar over what OpenTSDB provides from just pure aggregation of time series data. So after talking to James, we pursued a Phoenix-based back-end time series engine for Argus. It went really, really smoothly. Argus allows us to retarget our microservices relatively quickly with little disruption to our customers. It essentially took about 3 days of focused development between James's team and my team. The goal was to work around some of those OpenTSDB limitations. Briefly, we modeled time series data as a Phoenix view, leveraging the row timestamp optimization. Tag values inlined in the row key, and we get the benefit of using skip scan filter optimization, so we can really reduce the amount of the data set that we're exploring. And it importantly allows for secondary indexes on particular metrics and tags. So for those performance cases where we experience that performance cliff from high values for tags, this really helped improve that as well. Another benefit is that the metric and tag names are managed outside of the data as metadata, which is really great because currently we have to capture metric data in a separate table so that we can do wildcard expansion. But with Phoenix, we get that for free because it's already part of the metadata that gets collected when we store that time series into HBase. Going forward, one of the things that we're also going to explore is using Drillix, which is Phoenix and Drill, so that we can federate queries across data centers where we have Argus deployed in each one of those data centers, and also get the benefit of joining to those external data sources that we use where we're collecting other operational data that we want to correlate as well. Overall, it was a really great success. The write performance, you can see, is pretty much on par, a little bit better for OpenTSDB, but still in the same range. But this is using 2 clients in parallel, so we're getting around 15 to 22 million. This is close enough write performance, but the benefits of Phoenix for the other areas that OpenTSDB has shortcomings really provides a major advantage over just the pure write performance. Now on the query side, which is where our bread and butter is, Phoenix actually does really well. For small aggregations, OpenTSDB and Phoenix are relatively the same. Phoenix actually outperforms OpenTSDB by a little bit. But the real measure of success is when we're aggregating over a large number of time series. And here you can see that Phoenix performs much, much better than OpenTSDB for those large aggregations. Another benefit for Phoenix is that a lot of the aggregation all the aggregation for OpenTSDB occurs on the OpenTSDB client. So we pull all of that data out and the aggregation gets performed on the client. But with Phoenix, all of that aggregation gets pushed down to the region servers. And so the resulting network traffic that gets pulled back out to the client is significantly smaller. And by significantly, I mean almost nothing compared to what OpenTSDB does. Disk usage, obviously, with the amount of operational data we collect, the amount of storage space we use is an important factor. And here you can see that with Phoenix with fast diff and snappy compression enabled is similar to OpenTSDB. So everything considered, being able to use Phoenix really helps us to overcome those limitations that OpenTSDB has in it for our use cases. And it's been a really great experience so far. So the Phoenix implementation of our time series database engine is going to be added to Argus. Argus is on the open source community on GitHub, and we're happy to include that as well. We're just finishing up some final touches on it. And with that, I'm going to hand it over to Mas, and he's going to talk a little about performance.
Thank you.
Thank you.
You go. Okay. Okay, all right.
Hello, I'm Mas Suzuki from Sony, and I would like to talk about 5 major tips that we use to maximize performance on a 200+ SQL HBase Phoenix cluster. Okay, so first off, who we are and why we chose HBase Phoenix. We are a DevOps members from Sony's News Suite team. This is basically a newsreader, RSS newsreader application that comes pre-installed in Sony's Android devices. And we chose HBase and Phoenix because of 1, scalability, 2, SQL compatibility, and 3, secondary indexing support. Now, I just want to touch a little bit about our use case. Uh, our main primary use case is caching contents on a very temporary basis. There's two parts to this. One, there's a SQL read portion that occurs whenever the end user accesses his or her content, on the database. There's the other portion is the SQL write portion, where the fetcher server basically goes out and collects contents from outside content holders. So these are the two portions, or this is our basic use case. Now, I just want to touch a little bit upon the test, the performance test apparatus that we used and the results that we got. We were pretty impressed by these results, but first, the test apparatus, we used about 1.2 billion records. So these are 1.2 billion rows of data, and each of them were about 1 kilobytes each. We used 8 orthogonal indexes, and for our servers, we used about 200 region servers, 3 zookeepers, and 3 HMasters. For clients, we used 100 clients. For the test results, we were able to get 51,000 queries per second, which was at least it exceeded our expectations. And the response time was on average about 46 milliseconds. Now, so this is my last slide. These are the 5 major tips that we use to basically maximize performance on the cluster. Now, I will be talking more in detail in tomorrow's PhoenixCon presentation, but I just want to quickly run through the stuff that we utilize to maximize performance. One is whenever you use a secondary index, try to use, or at least use SQL hint clause when doing so. This gives you at least, well, in our case, it gave us a twofolds improvement in terms of performance. Why this is so? Well, this is still a hypothesis. We have not verified this with people like James and everybody else, but I believe an extra RPC, or remote procedure call, is issued when the client runs a SQL statement that uses a secondary index. Now, if you use the hint clause, this can be mitigated, and we use the version 4.3, but from the newer 4.7 series and beyond, there's a new parameter by the name update cache frequency. And we haven't tested this yet ourselves, but this may also work. Number 2, use memories aggressively, so to minimize disk access. 3, manually split region files if possible, but never oversplit them. 4, scale out instead of scale up, and avoid running power-intensive tasks simultaneously. So these are the 5 tips that we utilize. I'll be talking more in detail tomorrow, and yeah, we'll see you tomorrow. Thank you.
Thanks, Mas. Hi, guys. There you go. Hi, guys. My name is Vijay. I'm from eHarmony. I believe most of you guys know about eHarmony. We are a relationship service provider for people who are seeking for long-term happy relationship. We believe that key to the happy relationship is the compatibility. So how do we do that? So basically, we collect 150 plus data points from the user during the onboarding. And from these billions of data points, we calculate the compatibility score and all that stuff. And then we run our algorithms to generate the matches for the users. OK. Then we serve those matches to the users through our system. OK. So user has various requirements. Users tries to request the system with various filters. Like they want to retrieve the matches within the certain distance, and user wants to retrieve the matches whose matches have the photos and whatnot. At the same time, we have our batch system, which generates the matches, like millions of matches to the entire user base. Plus, whenever user changes any of your user preferences or address or whatnot, we need to notify all user matches, which is like It's huge. So, which is huge. So what is the problem? If you notice this thing, this graph, this is the response time for our main use case, serving the matches to the user, okay? So first of all, 95th percentile or 75th percentile is more than 1 second, which is not acceptable for the online system. Second, there are spikes. Response times are not consistent. During the batch period, all those writes are impacting the read performance, which means the batch layer impacting our read layer, which is not good. So that's the problem. So how did we solve the problem? Obviously, the problem here is there are multiple layers, right? And then the batch layer is impacting the service layer. We want to separate those layers. So there is a Lambda for the save. The Lambda architecture provides you the clear separation of the layers. It is good for the fault-tolerant system, linearly scalable, so on and so forth. So with this, what we did was we separated the batch store from the speed store. So the batch store, we choose the HBase, and matching system generates all those matches, and we'll go through the Apache HBase, Apache Kafka, and then the batch system processes those events and puts into the Apache HBase. So with that, whenever user tries to send the communication or whatnot, all the user events, they will be written directly into the Redis, and then we emit an event that will be asynchronously processed by the batch system and put into the HBase. So we decouple that system. But at the same time, if user request will be served with the query layer, where basically we get the batch data from the batch system, which is HBase, and the delta from the speed storage, which is Redis. And we merge that data set and present it to the user. Boom, what happened? There you go. So if you see that, the top graph is the get matches, which is serving matches to the user. So you can see it's a pretty consistent. Response times are pretty consistent, and system is very stable, and we were able to bring down the response times below 1 second. Our 75th percentile is 200 milliseconds from 800 milliseconds. That's huge. This is very important. Save matches. Because of that Redis, so we were able to bring down that response time from 4 seconds to 48 milliseconds, and it's very stable. So why HBase and Phoenix? We did the POC because it's a big system, and we already, we choose another key value store before, and we failed. So this time we carefully considered different various NoSQL stores, and finally we choose HBase because HBase is strongly consistent. Consistency is very important for us. Another thing is we want to apply the filters in store, not in service, because we don't want to deal with all GC problems and network bandwidth issues. So that's why HBase is the perfect solution for us. Apache Phoenix, of course, it's a SQL engine. Working with SQL layer is very easy, and it's a very consistent. And also it has, it solves so many problems for us. It has JDBC connectivity. It's abstracted so many aspects. That's why we choose Apache Phoenix. So to further reduce the development effort, we built this library, which is Phoenix HBase ORM library, which is basically, it's like a HBase library for the HBase. It's a ORM library for the HBase on Phoenix. So basically how it works is you annotate your entity bean, and then you register that bean, and then boom, that's it. We provide the interfaces so that you can write the DSL kind of queries, and you can execute them. It's pretty easy. So as part of that, we open source this project, and we are going to support it. So of course, in 5 minutes, I can't explain this big architecture. So I'm going to explain in detail tomorrow, what challenges we have, why we have to choose HBase over other stores and other stuff. So I hope you guys join tomorrow for the HBase conference. With that, I'm going to hand it over to Purnachandra. Thank you.
Hi, I'm Purnachandra from Cast Data, and I'll be talking about a new feature in Apache Phoenix, asset transactions using Tephra. So before we start, let's find out why we need transactions. Transactions have these property, all or none property, that makes writing distributed programs very easy. So when a client starts a transaction, it always sees a consistent view of the data at the time the transaction was started. And no matter you have concurrent updates to the same piece of data by other client, the consistency is not altered. And once you have a failure during processing, then you don't have to worry about the state of the system or about any partial writes that are being left behind, because the transaction failure will cleanly roll back the partial writes. This is especially important for Phoenix, where you have to keep data table and index table in sync for every update. So if you use transactions for the update, then either both the updates will go through or none will go through. So Phoenix uses Apache Tephra as a transaction engine. We know that HBase has strong consistency for operations on a row or for some batch operations within a region. But HBase does not guarantee strong consistency for operations across regions or across tables or across RPC calls. So Tephra fills in this gap by providing asset semantics in these cases. And Tephra is extensively used by CAS Data Application Platform, or CDAP, and from Phoenix 4.7, Phoenix uses Tephra for transaction. So let's take a very high-level look at Tephra's architecture. There are three main components. You have the transaction client, you have the transaction manager, and you have transaction co-processors running on the region servers themselves. You can have more than one transaction manager running for high availability. One of them will be active and the rest will be standby. When the active goes down, the standby will take over. And transaction manager uses Zookeeper for the leader election, and transaction client uses Zookeeper for discovery. Some more details about the components. Transaction client is some client that wants to do some data operations. So it talks to the transaction manager to start and finish a transaction. But once it starts a transaction, then it directly talks to HBase to do all the reads and writes using that transaction. And transaction manager's role the main role is to just create new transactions as and when the transaction clients ask for it. Transaction manager also keeps all the state of the transaction system, all the in-progress transactions, the committed transactions, and invalid transactions. And it also does conflict detection during commit time. And finally, we have the transaction coprocessor that runs on the region server. Coprocessors provide two functionalities. The first one is they provide read isolation. When you have multiple concurrent transactions going on, then they help in isolating the transactions. And the other thing is they act as janitors and clean up the invalid transactions or the transactions that are no longer visible on compactions. So Tephra uses snapshot isolation to implement transactions. A very brief overview of this. We know that every HBase cell is versioned using timestamp. So Tephra overrides the timestamp with the transaction ID. Now you have all writes done by a single transaction having the same transaction ID. This ID can be used for isolation by the coprocessor. So for isolation, the only thing you have to do is you have to exclude all the transaction IDs that are not committed yet. And Tephra doesn't use any locks on tables or rows for concurrency control. Instead, the competing transactions are allowed to proceed in parallel, and conflicts are detected during commit time. And if any conflicts are found, then the conflicting transaction will be rolled back and it can be retried. This kind of optimistic concurrency control is good when you can partition your data into disjoint sets so that each client is independent and they don't step on each other. So you'll pay a price only when conflicts occur, and if they are rare, then you'll have very high throughput. We did some very basic performance benchmarks using Phoenix Client on transaction tables and regular HBase tables. So what we found was transaction tables are slightly slower than regular HBase tables when you do operations in small batches. This is understandable because every transaction start, conflict checking, and commit needs 3 RPC calls, one for each. So if you do small operations in small batch, then the overhead will get distributed across the operations. So we saw that batch writes are around 2% slower than regular HBase tables, and reads are not very slow. we still plan to do detailed performance analysis. And the other thing that we did was we wanted to see how we scale with more writers. So as we see, as you increase the number of writers, we scale pretty well compared to the non-transactional table. And finally, let's talk about some future work that we are planning on doing. So as we saw that we have one active transaction manager at a time. So that can be a bottleneck if you want to do millions of transactions per second. But so what we are planning on doing is partition the tables into multiple sets and have one transaction per manager per table per set of tables. And the other thing that can be a operational bottleneck today is when you delete invalid data through major compaction that does not get reflected in the transaction manager state. That's a manual operation today. You have to figure out when the compaction ran and then ask the transaction manager to prune the invalid list. So that is going to be made automatic. So the transaction manager will periodically query region servers to find out the compaction state and then clean up the invalid list. And the third optimization that we are planning on working on is read-only transactions. When you have just when you want to do just reads, you won't have any conflicts, and you won't be making any changes. So there's no need to check for conflict. So instead of making 3 RPC calls, one for start, check for conflicts, and finish, you can make just one RPC call to start a transaction because you're only worried about consistency. So that will improve the performance a lot. And finally, there are some minor performance improvements we can do during conflict detection and then while appending to edit logs. We'll talk more about this in detail in tomorrow's PhoenixCon. Looking to see you all over there. Thanks. I'll hand it over to Maryann.
All right, I'm Maryann from Intel. Today I'm going to talk about Phoenix on Cal side. We started this work at the end of 2014 when we decided it's time for Phoenix to move on to a better compilation and optimization framework. And Apache Cal side turned out to be a great fit. So what is Apache Cal side? In short, it is a cost-based query optimizer which can basically be plugged into any SQL engine. So let's take a quick look at the integration model. So we're going to replace the entire Phoenix front end from parser validator to query optimizer with Apache Cal side. And then we'll have a translation process that converts the Cal side relational algebra to Phoenix query plan that can be executed in Phoenix runtime. And we're going to have some customization here on the Cal side part. We'll have Phoenix-specific SQL dialect plugged into Cal side parser, and also have Phoenix-specific optimization rules added into the built-in rule set. All right, so these are all nice features we already support in Phoenix runtime and in the existing standalone Phoenix compiler, like doing a range scan or a skip scan instead of a full scan. Like we have order by elimination, we have 2 join algorithms together with different aggregation approaches. But question is, how can we make the best decisions given all these nice options? Like for example, before we had to look for a where clause or an order by clause in a query in order to see if an index table should be used here in place of the original data table. But see, imagine what if a query comes in with a where clause that would favor the usage of the data table, while in the same time, it also has a nullify clause that would benefit from using an index table. So that's going to be a tough decision to make, right? But now that we are working with Calcite's cost-based query optimization framework, we can turn these optimization options into more generalized rules and find out the best plan out of all the outputs of firing these rules in all possible combinations based on single criteria cost. I'm gonna show you a very example of like what difference this cost-based optimizer is gonna make in the next couple of slides. But before we jump into examples, I'd like to highlight the other very significant drivers, motivations for integrating with Apache Calcite. So the first thing is this NC SQL support we'll get from Calcite just for free. So from this point on, Phoenix can continue to focus on making improvements in its runtime performance without having to worry about adding the missing grammar support. Next is materialized views. We all know that Phoenix already has secondary index, but Calcite has made it possible for it to support different forms of so-called indexes, like a filtered view or an aggregated view or even a joint view. Last but not least is the interop between Phoenix and all other Calcite adapters, such as Hive, Kylan, or anything, or JDBC sources or anything that works with Calcite. And in fact, we have implemented an initial version of Phoenix and Drill integration, which we call Drillix. And I'll give you more details in another slide shortly. So here comes the query example. Imagine we have two tables. One is the employee table, and the other is the department table. Our query is going to join the two tables together and output them in the order of department number. This slide shows what the existing Phoenix standalone Phoenix compiler is going to generate as the execution plan for this query. This is a list of things that will be done here. First, it's going to scan the build side of the hash join, which is the department table, and then send it over to the HBase servers and build hash cache. Then we do the actual join as we scan the employee table. As a final step, we are going to do a sort over the joined results based on the department number. So next, we're going to show you, this is how Calcite, as a cost-based optimizer, is going to do for this query. This is an illustration of the transformation from the original algebra to the optimized tree of physical operators. But due to the very limited time we have here, I'm not going to go through any details here or what's going on inside Calcite's optimizer. I'll cover that in tomorrow's PhoenixCon anyway. But just keep in mind here that this time the compiler chooses to do a merge join instead of a hash join. So this chart shows the exact difference between two query plans generated by the old standalone Phoenix compiler and the new Calcite Phoenix compiler. First of all, the scan of both tables is inevitable. So, but in the first plan, since it chooses to do a hash join, so the scan of the build side, the scan of the depth table has to be done prior to the scan of the probe side. While in the second plan, the two tables the scan of the two tables are performed in parallel. And also, like in the first plan, we have to send the results and build hash cache on the HBase servers. the overhead of which will depend on the size of the department table. And for each rows that comes from the employee table, we'll have a lookup cost. So here comes the most interesting part of this example. So apparently, a merge join doesn't have the overhead of anything to do with hash cache, right? But why would the old Phoenix compiler still choose to do a hash join anyway? So this is because a merge join requires like both sides of its child relations to be sorted on the join keys, which means it will usually introduce the very expensive sorting overhead. However, in this case, it happens that like one child relation, which is the department table, is already sorted on the join key, which is the department number, and and what's even better is that merge joins have this very nice attribute of preserving the order of their child relations. So that's why the second plan doesn't have this final step of sorting at all. So it turns out that the second plan only has to sort the employee table, while the first plan has to sort the overall joint results. I did a quick test on my laptop and got, the second query actually ran like 30% less time. But you should expect like, the performance difference to be even more obvious if we go with a bigger department table. So this is an example. To sum up, this is an example of, how cost-based optimizer manages to focus on the performance of the entire query instead of making local isolated optimization decisions. So now let's look at our drill. Let's look at our drill and Phoenix integration. So this is an example of how Drillix works with and group by aggregation query. So drill actually models aggregation as a multi-step distributed operation. And since drill and Phoenix now work under the same compilation framework of CalSite, drill can effortlessly obtain the table definition information in Phoenix, and it's also able to push down the table scan job as well as the first step partial local aggregation job down into Phoenix. And during runtime, the partial aggregation results returned by Phoenix, it's going to be converted into drill format and then be shuffled across drill servers and then serve as the input of the drill's final aggregation. Okay, so thank you all for coming to our presentation.